Hello and welcome to today's webcast brought to you by Power Engineering and sponsored by Conco Services Corporation. I'm Sharon Dotson, Associate Editor of Power Engineering Magazine. Today's event, the Total Condenser Performance Workshop, Leak Detection, will be presented by Gary E. Fisher, Sales Manager, National Markets of Conco Services Corporation, and Tony Laporte, Division Director, Leak Detection of Conco Services Corporation. Before we begin, we need to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We will try to answer these questions during the live Q&A portion at the end of this webcast. If additional resources have been provided for this webcast, such as a PDF of the slide deck, it may be downloaded via the Resource List widget that looks like a green folder at the bottom of your screen. You can expand the slide area by clicking on the Maximize icon at the top right of the slide area or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition many of the components on your screen, so please feel free to arrange as you desire to give you the optimal webcast viewing experience. If you have any technical difficulty during the webcast, please click on the Help widget. It has a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget and a member of our webcast support team will work with you to correct the problem. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.power-eng.com. And now it gives me great pleasure to introduce Gary E. Fisher.
Thank you, Sharon. Appreciate that, and welcome to everybody this afternoon to the Conco Services webinar on leak detection. Start out by talking a little bit about the goals of the power plants. Every power plant's goal is to maximize the efficiency and to produce the maximum number of megawatts capable at any given time. And to do that, they need to make sure that all the components are running at peak efficiency. And that includes your condenser and all the associated parts. And what we're going to talk about today is how leak detection and leaks in the system affect the ability of the power plants to produce megawatts. So the first thing we want to talk about is achieving the perfect balance of condenser efficiency and reliability. And what that is going to entail is a program where you have a cleaning, eddy current testing or NDE testing program along with a leak detection program to make sure that your system is running peak efficiency and so that you can make sure that you don't have forced outages, which are the bane of every power plant out there. And what we want to do is we want to maximize these strategies in order to maximize the megawatt output. So we want to make sure that your results can then be quantified and you can have an ROI calculated response. Now, if you take a look at this slide here, we're talking a little bit about achieving results of total performance. And really, total performance is a combination of cleaning, testing, and leak detection. And each one of these individual components is very important. Many of the power plants that we go to have a cleaning regimen. Many of them also have a eddy current testing regimen that they go through. Sometimes it's cleaning every year. Sometimes the eddy current testing, if it's a newer plant, is once every 5. As it gets older, maybe once every 2 years or so. But many of the leak detection programs that we run into are more on an as-needed basis. And we want to talk about how if you combine the cleaning, eddy current, and leak detection, how you can get a total performance out of your condenser and out of the condenser components. So let's start out pretty simply. Why do we need to test? Well, the condensers are designed, the design of the condenser is to be vacuum tight. However, there's going to be leaks into every system, and so condensers are designed with air removal systems. And these air removal systems are designed to allow for a certain amount of air in leakage that they can remove and yet keep the units running at peak efficiency. And it's whenever you have a leak into the system that exceeds the ability of the air removal system to remove that air that you get into a problem where it runs into a problem of efficiency and effectiveness of the condenser itself. So leakage of air and water into the condenser, it adversely affects your system when you exceed the air removal capacity. Now, how do you know? When do you need to test? These are some of the things that you've concerned with, some of the questions that we get. When do you need? Well, you're going to have an increased plant heat rate. That certainly gives you an indication that there's a problem, and it very well could be a leak test. You could have increased risk to turbine components if you see that you're having extra maintenance on systems. You could run into a situation where equipment begins to fail, where you're not getting the achieved results that you want from the associated equipment. Because as you allow the air entering the system and into the steam space and it's unable to be removed, that gets entrained in the condensate. And then as it passes down through the feed water system to the boiler and to the other equipment, you get corrosive conditions that will exist throughout the entire path. And if you don't deal with these O2 levels for a long period of time, you're going to affect the component's life and you're going to decrease the efficiency. So it's very important that this is removed because you can increase the risk to the turbine components. High level of dissolved O2 feed water systems, as I just mentioned, as they get entrained in the system, they become a real problem for the rest of the equipment down the line. So when do you need to test? And this is something that's quite interesting for us. This is typically how we get the call, and that's a reactive test. And that happens whenever you have a leak. The telephone call comes in, and it usually comes in sometime in the summer, sometimes when you're pushing the unit to its maximum capacity. And the call comes in that we've got a leak, and either I can't meet my megawatt output or the unit is down. When can you get a crew out here? And when can you provide the services that we need to get this unit back up and running? It's a reactive test that really puts you at the wrong end of the spectrum. The condenser is now telling you when you have to spend money to come out and fix a problem. And this, in many cases, becomes a much more expensive way of solving the problem. It's one that you're being pressured to resolve. You've got to get the megawatt outputs back up. You've got to get the unit running. And so you have to spend whatever is necessary in order to get a crew out there to do this test, find the problem, and then resolve it. And this is something that's going to happen throughout the life of your condenser. However, there's another way to do it also, and that is a proactive test. And we do not see this very often. But a proactive test is one where you go into a routine inspection. Now, many of you out there are going to say, when do I have time to do a routine inspection? Or when do I plan for a routine? What do I look for in a routine inspection? Well, we have a solution or a potential answer to that, and that what you do is before you go into one of your outages, you call a leak detection crew to come out and test your system. Find out where you have leaks. And they may be relatively small leaks at this time, but they're leaks that you can address right now because you're going into an outage. And while in this outage, you can then resolve the problem before it becomes a real problem. Also, after the outage, after you've done all your tweaking, after you've gone in and changed the valves, reset seals, whatever you have to do, it would be good to spend that little bit of money to have a leak detection crew come in and do a test on your system while you're bringing it back up to speed so that you can identify one of the leaks or a leak in the system itself and resolve that problem before you push this unit to its maximum capacity in July. Because that's when you go back to the reactive testing. That's when the problem really occurs and you're starting to lose megawatts, and thus you're making that call now to come on out and resolve the problem on an emergency basis. So a proactive test would fit right into a program where you could be ahead of the game. Now, what are some of the condenser leak indicators? Condenser back pressure climbing. Now, this is not just an indicator of necessarily leak detection. You could have other issues with your condenser, such as fouled tubes in the condenser. That could cause a back pressure climb. But over a period of time, as you do a cleaning in your unit, you will have a pretty good idea how clean the tubes are at any given time. So the system engineer, the maintenance person on that particular piece of equipment will be able to determine if that back pressure is related to a fouled tube or possibly air leakage. And air leakage is really a pretty clean, efficient, effective, and inexpensive way to go in and do a test to make sure that this isn't the problem, and if it is, to resolve it right away. Also, to monitor your O2 levels. When you see that the O2 is going up, of course, that's a problem unto itself. This is really an air leakage situation, so that's something else that you're going to be monitoring. Or a change in water chemistry. Most of the chemists in every plant that I've been to monitor their water chemistry quite often. They have a very good handle on it, and they want to make sure that any change in that water chemistry doesn't relate back to air leakage. And possible there is an increased use of phosphates, which would come back and give you an idea that we have a leak in the system, and it's something that we have to address right now. So where can you have these leaks? Where are these sources of leaks? And this is one of the areas that really is quite concerning if I were to be a plant. And this is one of the areas where I want to bring in now that it's critical that when you bring in a leak detection company that you make sure that they are experienced. Because when you take a look at the number of sources of air leakage, you want to make sure that the team that comes in has a very good idea where to look after asking some questions of the plant personnel so that they can minimize the amount of time that they're on site and to resolve the issue. So when you take a look at it, you could have in-leakage to a shell, you could have ruptured discs, shaft seals, test probe penetrations. And that's an interesting one in that if you think of today's market and today's where we're heading in technology, we've got more sensors tapped into the system itself than ever before. These sensors may be just providing data for you, or they may be tied into some automated system. But any one of these test probe penetrations, anytime you penetrate the system itself, you're going to run into a situation where you have a potential leak. And manways, vacuum pumps, flanges, and the one that I'm always amazed at, bolt holes. How many bolt holes do you have in that system right now? And any one of them has the capability of being a leak. So you want an experienced crew that's going to be able to come in and ask you a certain number of questions, and that will give them an idea where to look so that we can minimize the amount of time on site, minimize your bill, and get your unit back up and running. Now, water and leakage. Primarily here, you're definitely in the water stream itself, but in most instances we're going to be looking in the boxes. And the sources of water in leakage can be water box flanges, faulty tube plugs. We run into this quite often, and the faulty tube plug could be any number of situations. It could be that you have the wrong plug in the unit itself. It could be that you put a temporary plug in that unit with full intentions of removing that and putting in a permanent plug at a later time. Only time has slipped away and you have forgotten to do that. So that plug is now deteriorating, and you're asking a temporary plug to be a permanent one, so you can have a leak. It could also be that you've put in a removable plug, and so the torque on that particular plug has now changed, and so the plug itself is now leaking. So any type of faulty plug, installed wrong, the wrong type of plug, hasn't been adjusted or set up properly, or has just faltered as far as the torquing goes. Leaking hot well components, through wall penetrations, and through wall penetrations can be very tricky. These are the types of leaks that when you're under pressure and temperature may occur, but when you bring the unit down and that temperature decreases and the pressure decreases, that they seal back up. Again, an experienced crew will be able to find these leaks much quicker and much more expedient manner than an inexperienced crew. And then the tube-to-tube sheet joints. And the one that's missing on this slide is the tubes themselves. Of course, you can have a leak in the tube, and if you have an eddy current test, you'll be able to identify maybe those tubes ahead of time. But if not, maybe you have a tube that's going to have under deposit corrosion, and what has happened is eaten away at the tube itself. And so now you have a hole in that tube, and that fails, and you have a leak. Also, that tube-to-tube sheet, for any number of reasons, that tube-to-tube sheet leak can occur at any time. So it's something that has to be checked, and whenever that condenser comes down, of course, somebody should be taking a look at all that. Now we're just going to go through a series of slides here that just show some pictures. And what these pictures depict are areas that you could have a leak. And basically taking a look at the first penetration of a pipe going through, if it's any penetration into the system, it creates the potential for a leak. And if you think how many pipes you have going in there, you can be quite amazed at how many leaks you don't have. Here's where a crossover bellows. This situation, out of sight, out of mind. It's quite high up in the air. You don't go there very often, and yet it has a great source or a great potential to have a leak in that particular area. Difficult to find, and maybe one you're not considering. Test probe penetrations. As I mentioned before, we just see more and more of these test probes. As we gather more and more data, as we want more data to run more pieces of equipment, we always put test probes or sensors into the system itself. And with each one of these connections, you introduce a potential for a leak. Shaft seals. In this particular case, this is a low-pressure turbine shaft seal. And I take a look at all those bolts there and think any one of those bolts, as you go in to change any of those seals or maintenance, if they are not tightened down properly, you can have a leak right there. Or how about the heater pump shaft seal? So you have any number of shaft seals or seals in the system itself that could be a potential leak. And again, the experienced crew can help you resolve this problem before it becomes a real serious issue. Now, choosing the proper ideal tracer gas. Before I go into this, though, I want to talk a little bit about the old leak detection methods, some of them that were used years ago that are still used today. And in some instances, they are effective. Some of them being like smoke, sight and sound, the ability to hear the leak, getting close to it, understanding where that is. Plastic wrap. We've seen this many times where plastic wrap is put over the condenser tubes, and you determine where that leak is by that plastic wrap being pulled into the tube itself. And shaving cream. These are all methods that are used. They are still used today in situations where you are under the gun. You've got to do something immediately, and so you're trying to do something right there on site with your crew members. And in some instances, they pull out and they work for you. However, they also have shortcomings. It's really unreliable. They're inaccurate in many instances, and they're unrepeatable. And one of the problems that we've seen on the unrepeatable side is that you do the test, you find the tube or you find the leak, or so you think, you repeat the test, and all of a sudden the leak isn't there. So what is it? Is there a leak or isn't there one? And that becomes a real problem to identify where it is. And so here we come with the use of tracer gas. And so you want to choose one of the tracer gases, and really there's only two. I'll put both of them up here now. There's helium and there's sulfur hexafluoride, SF6. Both are used in certain specific applications. I'll say that helium is probably used 90% of the time. It's used, it's less expensive, and it's more prevalent. However, again, you want to make sure that whoever you hire to come in to do the work for your leak detection contractor, that they are capable of handling both of these gases, because you never know when you're going to run into a situation where helium isn't optimal, but SF6 is. And you don't want to have to call a second contractor in who can handle SF6 because your primary is incapable of using it. So these are the two gases that are used and in the industry today. So let's talk a little bit about air in leakage. What do we want to know about it? Well, we would like to know the total amount of air in leakage. How much air are you pulling in? Is it a substantial amount? Has it been over time? Has it been a slow increase, or has it been a sudden increase? A lot of people have rotometers or some sort of sensor on the system, and if you have this, that will be able to give you this information, and then you can pass this on to your leak detection contractor so that he has some idea what he's looking at. Characteristics of the specific leakage. They're going to ask questions concerning specific characteristics. Where's it at? This may tell them that, hey, it's below the water line. It may tell them that it's associated with a tube, or it may be associated with a bellows, or maybe associated with those sensors. But specific questions and specific answers about the leak itself can give the characteristics that a leak detection contractor needs to narrow it down. And of course, dissolved oxygen considerations. As I mentioned, dissolved oxygen comes below the water line, and that would be an instant clue to your leak detection crew as to where the problem exists and where they've got to go to resolve it. What about water in leakage? Well, the condenser tubes themselves could possibly be leaking, so online injections may be needed. And this would be an instance where many of you have condensers with a variety of boxes. Maybe you have a 2-box or 4-box or 6-box unit. In that particular situation, the first thing you want to do is you want to determine which box you got to be looking at. Where am I going to go to find this particular leak? So you do an online injection. And we'll talk a little more about that a little bit later. But that will identify the box that you're going into. Once inside, you want to do the tube sheet inspections, and this is where you're going to come in and you're going to use helium. And this is going to be a system between the man out, the technician out in the field, and the one by the analyzer to determine which tube it is, and while you're doing the tube sheet inspection. And again, the leak characteristics. Is it a large or small leak? Is it a tube, or is it a tube-to-tube sheet leak? And all these types of characteristics lead to where the problem resides. So if we talk a little bit now just about the gases, and we were talking about the helium. Helium mass spectrometer, it was initially developed in the Manhattan Project during World War II, and it was designed specifically to find small leaks in the gas diffusion process. After the fact, it was used in a variety of other instances, one being the power market, to find leaks within the condenser within a power plant. One of the nice things about helium is that it's quick, it's reliable, it's non-toxic, it's non-hazardous. Relatively easy to get. A little more difficult today than it was years past, but still easy to get, easy to have in the plant itself, and easy to use. It's quite sensitive. The detection range itself is in parts per million, so it's a sensitive gas. You don't need a lot of it. It's a couple puffs to determine where the leak is, and you'll be able to pick that out of the system. It's suitable for most leaks, and we'll talk a little bit about this as we go on, but like I said, probably helium is used in 90% of the applications, and most leaks can be found with helium with an experienced crew. Talk a little bit about SF6. SF6 was an airborne tracer gas, and it was used to track plume migration back in 1976. Now, for some of you, that's like ancient history, but for me and some others out there, this is a relatively new type of operation. 76 isn't that long ago for me. And EPRI was the one that decided to explore its use as a tracer gas used in a power plant for leak detection. So a little bit about the SF6. It's inert, it's odorless, and incombustible. Again, all great features that make it of use. It's very sensitive. If you remember the last slide, helium detection range was in parts per million. SF6 is parts per billion. So you use less gas, and it's also capable of finding very small, minute type of leaks that maybe helium cannot find. It's non-reactive to H2O. I was talking a little bit before about if you're trying to test for a water leak and you have a condenser with multiple bundles. SF6 is the ideal gas to inject into the system below the water line because it's non-reactive to H2O that would be able to identify which bundle is the problem. And finally, suitable for small or hard to locate leaks. One of the real keys to this, though, is once again having a contractor familiar with both and a contractor that's going to be able to come out, analyze the problem, work with you to decide which gas they need. 90% of the time, helium. But in those 10% of those instances where SF6 is required, it's always great to have the contractor know how to use it and how much. So if we take a look at these two systems, helium and SF6, really they're very, very similar. The mass spectrometer on the left is for the helium, the fluorotracer analyzer is for the SF6. And if you notice there, the air monitor, the desiccant dryer, the strip chart recorder, they're all the same. You need all those, regardless of what type of gas you have. The difference here is in the analyzer itself and the people that are utilizing it. So they're very similar, they're very useful, but they also serve their own specific purpose. So now you've got your crew out there, you know you have a leak, you've got some of the characteristics of the leak, you're determined an area that you want to inspect. What does the contractor need? What do you need to provide so that that leak detection contractor can come out and provide for you a good, solid report? Well, you're going to need some power. And we're saying a minimum of 15% turbine power is required. And why is that? Well, because it's the steam that drives the gas down through the system. And so if you don't have the steam, you're going to end up with the gas just floating on its own. You're going to end up with pockets of gas, and you may never reach the leak, especially if it's downstream. So you need some power. 15% turbine power is crucial to a successful leak detection as it drives that gas down the system. It also clears out the tracer gas out of the condenser. You don't want pockets to occur because then you get false reads. If you get a false read, now you're trying to fix something that doesn't need fixed. You get a much quicker response time as the system drives the gas down through all the networking parts. You can find a leak quicker as this gas moves down with power behind it, and you get a quicker recovery time. And the last one, without steam flow, hey, the tracer gas background continues to rise. And that's one of the concerns. That's something you've always got to watch for. Again, an experienced crew capable of taking a look at that, analyzing that, and making sure that you have enough power and that that gas is being moved out and that you're not getting false reads. That is something that you don't want to run into. Now, if we just take a look at this slide here, typical leak response, and if you look at the response on the y-axis and the time on the x-axis, this is what we're going to see back at the analyzer. Here's what it's going to take a look like. And this is, once again, hate to keep bringing it up, but where experience really comes through. Because leak detection, in many ways, is a mixture of art and science. There's science to it, but these people with experience have an artwork around it, and they're able to interpret this data to tell you exactly where they are and what the problem is, to give you as we go through this, I'll give you some examples here. But at any given time, as you go down through the system, the technician out in the field is giving a gas release, releasing the gas into the system, either at the tube sheet if they're doing water, or maybe out in the plant around the penetrations of the pipes or the sensors if they're looking for air. There's a gas release. And then there's a response time. And that's the time it takes for that gas to go down through the system and to be picked up by the analyzer and alert the technician at that analyzer that we have a hit. And that time could be anywhere from 20 seconds to 30 seconds up to a minute, depending on where the leak is, how big it is, how far away it is. So there's a response time. And there's your initial response. So from the gas release to the initial response is response time. You then get a rate of response, and this will tell the technician back on site where you are and what's going on. It also gives you a magnitude of response, and this will give an indication of the size of the leak. And then there's going to be a clear out time, and this is the amount of time that the steam is driving the gas through the system and clearing it out so you don't have any pockets and you get back to your baseline. And then, of course, you got your strip chart recorder. So if we take a look at this slide by itself, this is why the strip chart recorder is so essential to the process. You've got a technician who is out in the field. He is either in the box at the tube sheet or he is going around the plant trying to determine where the air in leakage is. And you have a technician back at the analyzer. And the strip chart recorder, based on this type of graph, can tell you when you're getting close to a leak. The rate of response may not be as sharp. It may be very gradual, which means that you're close to the leak, but you're not there. Of course, the time between the gas release and the initial response has been already told to the field technician, who is now going to backtrack 30 seconds, 40 seconds, whatever he's told, and move back along that line to determine exactly where the leak is. As you get closer to the leak, this rate of response increases, and the strip chart recorder can tell you when you have hit that leak. It can also tell you when you've passed that leak. And of course now it is all in the system. You all have a dedicated report right there, if you will, that gives not only the technician the ability, but you the ability to see where that leak was, and whether it's a valve packing or the valve itself or some other problem. The strip chart recorder gives you the ability through this information to determine where the leak is. And if we take a look at the next slide here, this is exactly what it's going to be looking like. The person on the right is the technician at the analyzer. He's there reading the strip chart recorder, and through headsets, he's speaking to the technician out in the field, who in this instance on the left is using helium and puffing helium into those pipes or into those protrusions into the system itself. So they are in constant contact, so they know exactly where to go to solve the problem. Now, condenser tube leaks are a little bit different. You basically have the same type system. You have the guy out in the field. You have the technician back at the analyzer. You still have your recorder. You still have your prick chart. So that is all the same. But when you get into the condenser itself, after you've determined the bundle that you're going into, you use plenums. And these plenums vary in size. And these plenums range from 1 foot by 2 foot to 1 foot by 1 foot, down to a small 4 by 4, and then showing in that picture the gun or the individual tube sensor, so that you can narrow it down to the tube that is a problem. And the way that you go about this is you start in a specific area, say the upper left-hand corner, and you give about a 10-second shot of the helium, and this is all done with helium. 10-second shot of helium, and then you transverse that tube sheet covering every tube. Once you have a hit, you go back to that particular area and you reduce the size of the plenum from a 1 by 2 to a 1 by 1. And then you go down to a 4 by 4 inch, and then finally tube to tube. and you can then isolate the tube or tubes that are giving you a problem have the leak. If by some instance you know you have a leak, but the individual tubes are not showing any leak within, then it's a pretty good guess that what you have is a tube-to-tube sheet leak, and we can address that differently. So this is a bit of a different on the leak for tubing rather than if you're doing air. Now, this is what it would look like. This will be a depiction of setting up inside the condenser and doing a tube sheet inspection. If we take a look, we've got the inlet water box, we've got the outlet water box with the air mover. You have the air removal system coming up into the condenser off gas. A sampling pump is then set up to sample some of that condenser off gas, and that goes through a sample conditioning and through a gas analyzer. And the way this works is the plenum, which is now in the inlet water box, is held over a batch of tubes, and gas is sent down those tubes to the outlet water box, the air mover pulling that gas down the tube. In this particular instance, we have a leak in a tube, and you can see that leak as it goes out and gets collected through the air removal system into condenser off gas. That, in turn, is picked up by the sampling pump, which sends it back through the sample conditioning over to the gas analyzer, where the technician monitoring the analyzer senses the leak and tells the technician out in the field that we have a leaking tube or a leak of some sort at that point. Now, this is the online injection SF6 tracer. And where we use this, again, this is to be injected below the water line. Again, for those of you that have multiple bundles on your condenser, you connect below the injection point, below the water line. You inject gas at about 10 CFM, about 30 seconds, and this can identify the leak in the particular bundle. Now, you have the ability to shut that bundle down in order to go into that particular area, reducing the amount of time it's going to take to find the leak. And it's capable of identifying down to about 1 gallon per day, so it's quite small. Now, before I end this on the summary, let me also state that we've talked today about water-cooled condensers, but we can also do leak detection on air-cooled condensers. And so if some of you have plants with an air-cooled condenser, this is still viable and a feasible way of finding a leak. Of course, you have different obstacles in an air-cooled condenser, most notably the size of the condenser, the height of the condenser, the amount of pipe that you have in that condenser. But again, an experienced team can find the leak within that air-cooled condenser and been very successful. We have been very successful at finding these in various locations that have air-cooled condensers. In summary, air and water in leakage, it costs generators hundreds of thousands to millions of dollars a year. And that can come in from megawatt reduction to loss of megawatts while the unit is down, to repair costs on the unit itself, especially when it's an emergency basis, to wear and tear on equipment if you get O2 into the system and that moves down there and it causes problems. So you may have a pump or you may have some piece of equipment that's designated to last 10 years that may, in actuality, last only 7 or 8 because of that, which will increase your overall costs. So it's costing you a lot of money to have leaks in the system and not identify them. In fact, condenser tube leaks cause more than 6,000 forced outages annually, and they rank as one of the highest concern among plant chemists. And I'm sure in any instance when you have a forced outage, that's not a good situation for you as well. Management's got to be unhappy. The pressure is on to get the unit up and running, and boy, it would be a lot nicer, a lot easier on you if you could identify this problem, potential problem, before it occurs and becomes a huge problem. So in addition to a reactive leak detection program, we are promoting the proactive regimen of testing that keep the total air in leakage in check. And many times you'll have a contractor come out and say, listen, if I don't find a leak, then we won't charge you. Well, you're going to find a leak because all systems have a leak. The question is, and the real issue is, to find the right leak, the one that's causing you the problem, the one that's going to be a real nightmare for you. So if you can do a proactive regimen and you can set up a program prior to your outage, after your outage, or at some other time, you can identify a leak that has the potential to be a real nightmare for you when you're pushing that unit to its maximum capacity. And the real beauty to leak detection, its ROI is very good, very good. So the recovery that you get and the response that you get monetarily is in the 1,000% range as compared to the cost of the leak detection process. So this is our discussion on leak detection. We appreciate you being here for the discussion. I see that we have some questions, and we are going to turn those questions over to Tony Laporte. Tony Laporte is our division director in the leak detection division and has many years' experience. So I'm going to turn this over to Tony and have him answer your questions. Thank you for your time, and I appreciate it.
All right.
This is
thank
Tony.
you, Gary, very much for. Hi, Tony. Thank you very much for your presentation, Gary. And just a reminder to the audience, if you still have a question that you want to ask, click on the Q&A widget, and we will try to get to it. So, Tony, let's start with the first question we have here. Another source of air in leakage that we discovered was the turbine LP bearing pedestal train line, I hope I said all that right, where the routing of this piping was internal to the condenser exhaust hood. Oh, I'm sorry. That is actually the wrong question. Sorry. All right. Sorry about that. Say for a single 500 megawatt plant, how much would it cost in money and time to do an initial assessment of a plant the first time with no previous data, etc.?
A 500 megawatt plant usually takes about 8 to 10 hours first time in. Costs would depend on, labor-wise, you're probably looking at about $3,000 per day, plus expenses depending on where you are, California, East Coast, West Coast. So the answer there is about $3,000 for labor and equipment, and plus expenses, and 8 to 10 hours for a 500 megawatt unit.
All right, thank you. Yes, we have quite a few. SF6 is banned as a tracer gas in Europe due to its global warming potential, which is roughly 24,000 times that of CO2. Has the use of SF6 as a tracer gas been affected in the U.S.?
Not as of yet. There are questions about it, and some of the plants do not use it. And so, but it hasn't been banned in the United States.
All right. Multiplier for emergent leak detection services versus routine periodic inspection on average.
I don't have a specific number, but I think Gary mentioned something about the ROI on preventative leak detection as opposed to coming out when the plant is down and the dollars lost because the unit was lost because of an air leak.
I think the big thing there, if I may interject, one of the big costs there isn't so much the manpower as it is trying to get them there. When you have a planned program, it's easier to schedule around events, easier to get airfares or easier to travel, and you can pick less expensive ways to get to your site. And then you can work around whatever you're doing at the plant in order to make your costs less expensive as possible. When you're on a situation where you have an emergency, you're at the mercy of the airlines. or whatever to get there in the quickest way possible at whatever time of the day to get to the plant, and then to really do whatever is necessary, which may have some added costs. So I'm not sure there's an exact number to that, and it depends on the size of your plant as to how much costs are. But there's certainly, when you have a reactive unit, it's going to be potentially more expensive than if you did a proactive. And of course, then on a reactive, the unit's probably down, or else you don't have megawatts producing, whereas on a proactive, it's planned going down, so you don't have any of those associated costs.
All right, thank you both. Next question is, in your experience, what are typical plant response times to condenser water in leakage events? And can you give some examples of time for leak identification, time for water box isolation, or time to detect the leak using SF6 or helium?
Typical plant response for condenser tube leakage is they wanted you there 20 minutes ago. What we usually run into is a situation where they know they have the leak, or they don't know which water box it's in. We'll take SF6 and we'll determine which tube bundle it's in by shooting the SF6 into the circ water on each box. The tube bundle isolation or determination of which tube bundle is leaking probably only takes an hour or two. Going into the water box, depending on how many leaks they have, you may look at an 8-hour shift. Usually, we're in and out of there within 2 to 4 hours. Dropping one box and then going into another is different in each plant. Some plants, it takes them 8-12-hour shift. Other plants, they can do it in an hour. So the answer is variable, but typically, once we get into a box, we're out of it within 2 to 4 hours.
All right, thank you. Next question is, we have AL6X condenser tubing seawater service. We have seen very small pinhole type leaks, 0.06-inch pinholes. They are very difficult to find with helium leak testing. Are there better methods available to find these small pinholes?
One of the things we run into quite often is that with these very small leaks, you've got to get into the box as soon as you can after it's dropped. A lot of times we'll go into a plant and the box has been out for a shift or so, and these things, like Gary had said, have a tendency to disappear. These little leaks have a tendency to disappear. So what we like to do is we like to be there while they're dropping the box, get all our equipment set up, and get into that box, set up the air horns on the outlet side as soon as possible, jump in, and start looking for the leak. We found that the smaller leaks can be found if you get into that box within a very short time after dropping it out. That's been our experience. Now, let me just add, people ask, why don't you use SF6 then if it's so sensitive in the water box for the small leaks? What happens there is we have a gas dilution module for when we go into a water box with SF6, and we have to dilute the SF6 because the good thing about SF6 is it's very, very sensitive. The bad thing about SF6 is that it's very, very sensitive. So you have to dilute the SF6, shoot it down the tubes, and in that case, the dilution brings it closer to the same sensitivity as helium. And helium is a lot easier to work with in the water box situation. So that's why we use helium. Okay?
Okay. All right, next question. It was mentioned that some historical methods of detection, such as plastic wrap or shaving cream, were often unrepeatable. Could you elaborate on why that is?
A lot of that stuff, that type of testing, like smoke, the saran wrap, the shaving cream, is very heavily operator dependent. You've got an operator who's been standing in that hot water box for a couple of hours looking for one tube leak. He gets frustrated, and all of a sudden he starts seeing leaks all over the place. And instead of plugging one or two tube leaks, you wind up plugging 20, 30, 40 tubes. And we've seen this on a number of occasions. With helium or tracer gas, it's yes or no. It either is leaking or it's not leaking. So you're not plugging something that's not there.
All right, thank you. And next question is, would you recommend every organization to develop an in-house expert to detect air and leakage?
I'm going to be truthful, very truthful with you here. What we found I've been doing this for some 36 years. And what I've found is that plants go into creating their own leak detection department. And it's a very good idea. But you usually have one guy who is gung-ho, so to speak. He wants to do it. He wants to get in there. He wants to find the air and leakage. He wants to find the tube leakage. And he's the main driver of the whole program. 1 or 2 years down the road, since this guy is so gung-ho, he's going to get promoted. And the next guy comes in, and he's not as gung-ho. And we see this on a consistent basis. In some plants, I think Wisconsin Power was the only one that I saw a fellow by the name of John who made it successful and stayed there for a number of years. I think he just recently retired, but I don't know what's going to happen there now. But brutally honest, that's what it is. The guy who initiates the program is very good, and once he moves on to bigger and better things, for the most part, people behind him don't want to be bothered with it. It's not a pretty job. It's hot, it's dirty, and a lot of people don't want to get involved in it.
Okay. Next question. We are seeing high dissolved oxygen in our deaerator inlet after low pressure heater number 4 sample, but have low DO in our sample after low pressure heater number 5. What could be the cause of this leak?
First question I'm going to ask is how high your air in leakage is. What I'd like to do is bring this up after the conference and talk to you personally about it, because there's a number of things that could be going on there.
Okay. Let's see. Next question. What is a typical test shot response time?
Typically, what you'd like to see, once you take your test shot, 3 seconds or so into the condenser vacuum, 30 to 45 seconds. That's what we really like to see, and in most instances, that's what we do see.
Okay, thank you. And next question is, do you have much experience with shaft seal in leakage? What percentage of your projects have found them?
Shaft seal. We find a lot of them. In most power plants, you find the shaft seals leaking. And as a matter of fact, a lot of times we can't take a test shot, or the plant operators don't want us to crack a valve or have one of their people crack a valve to take a test shot. And we typically use a shaft seal. We'll go down on the turbine deck shooting the shaft seals until we find one that's leaking to get our test shot in. So this way we know our equipment's working. But shaft seal leakage we see quite a bit of.
Okay. Why is an increase in use of phosphates for water chemistry an indication of air in leakage?
Gary, can you take that? Are you there, Gary? I don't know. I don't have the answer to that. I know I heard Gary say that in the presentation, but I'll have to pass on that. We'll find out what the answer is and get back to them.
All right. Thank you, Tony. And next question is, for air in leakage inspections, how long do you typically spray helium on each item? And do you spray one item at a time and wait for a response?
As we're doing air in leakage, you're spraying maybe 2 or 3 seconds each item, a valve, a penetration, or whatever else you're spraying, and you keep moving along. The fellow who's spraying tells the man who's sitting at the mass spectrometer he's on and when he's off, or when he's shooting and when he's not shooting. The guy on the mass spectrometer, as soon as he sees an indication, will tell the man who's shooting to stop, and they backtrack to isolate the leak. Is that the entire question?
Yes. Yep.
Okay.
All right. Thank you. All right, next question. Most plants have 2 vacuum pumps for their condensers. In your experience, have you found many leaks in the spare pump? And what items do you check?
Well, we'd like to, if one pump is not running, we like to swap them out to see what's going on, because if both of them are running, we want to do we want to sample from both of them, because there are parts of the condenser that may not be covered on one side, or one pump, not on the other. So we spray everything on it. One of my things from 36 years ago was to tell my guys as we trained them, if it doesn't move, you spray it. Because if I had a nickel for every time somebody told me that can't leak, I'd be sitting in Maui. You spray everything. Helium is cheap.
Okay. How do you isolate a tube-to-tube sheet leak?
I think Gary covered that pretty well in the discussion. And it's basically when you down to the 4-inch by 4-inch plenum, and you have maybe 4 or 5 tubes left, you get down to your single tube tester, you stick it in the tube, you shoot the helium down for each of those 4 or 5. If you don't see anything, you know that there's a leak in that 4-inch by 4-inch area, so it's got to be a tube-to-tube sheet leak. And by using maybe duct tape, you can isolate the exact tube-to-tube sheet area that is leaking.
Okay. Next question. What is the purpose of the air horn in the outlet water box?
The air horn, it's really important. A lot of people think we just use it to cool down the inlet side. But basically what you want to do is you want to draw the helium down the tube and exhaust it out of the outlet water box. You don't want the helium to accumulate in the outlet water box, because obviously you're looking for a vacuum leak. And if the helium accumulates in the outlet water box, it can get sucked back in. And all you're going to be doing is seeing cycles of helium in shots. And you're going to get repeated. So you want to get the helium out once through and out. But then you got to be careful you're not, exhausting the helium that's in the outlet water box to an air leak outside of on the turbine deck or something. So you got to be careful of that, and you've got to know that that's a possibility, and don't go chasing an air leak when you're looking for a tube leak.
All right. Thank you very much, Tony. And we are nearing the end of the hour. On behalf of Power Engineering and Penwell Corporation, I would like to thank today's speakers, Gary Fisher, Sales Manager, National Markets of Conco Services Corporation, and Tony Laporte, Division Director of Leak Detection with Conco Services Corporation, and our sponsor, Conco Services Corporation, for today's presentation, the Total Condenser Performance Workshop Leak Detection. This presentation will be archived within 24 hours and can be accessed from the home page at www.power-eng.com. A reminder email message for the archive will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.